Hey everyone, welcome back to our unit on geologic time. If you remember from last night's notes, we learned about Steno's laws, which included how we can order layers in terms of their relative age to each other. So we used principles like original horizontality, the idea that layers are always deposited flat first, superposition, the idea that younger layers are on top, laws of inclusion, saying that older layers can be included in other layers, cross-cutting relationships that show that layers that cross across other layers are younger, and contact effects, which allows us to order events that cause layers to be baked or chemically altered from others. So tonight we're going to learn a little bit about the idea of missing information. Like what happens if you're missing information from the rock record? This is called an unconformity. Those are intervals of missing time from a rock sequence. Usually this is because, and it's fairly basic, the rate of erosion is higher than the rate of deposition. So anytime you're depositing rocks, but they're being worn away faster than they're being deposited, you're going to be missing that layer 2-3 million years down the line. We tend to lump these missing layers or these changes in layers into three groups. Angular unconformities, like you see here in the image I'm pointing to with my arrow. Non-conformities, which you'll see here as a contact point here between this igneous rock blob below and these more ordered sedimentary layers on top, and something called a disconformity, which does not have a really strict visual appearance. We'll talk about that in a minute. Disconformities are hard to pick out unless you can actually find the age of the rocks, okay? So let's get into an angular unconformity, because the idea here is that we can learn things from them. We can actually learn about things that go on in an area. So angular unconformities happen over time. If we use the law of original horizontality here, in this image, we see that these flat layers of limestone are being deposited over time. And so the environment changes into a drier one over here, and something tilts or angles the rocks. So some event angles the rocks and it folds them up. So we get these angled layers here, and then the environment changes again. Sorry, I can't spell. The environment will change again into one that allows for flat layers to be more sedimentary layers to be deposited on top. So this contact point between these two angled layers and the flat layers on top, this is known as an angular unconformity. Okay, so here's an example. Let me erase all my images here. My writing. This is an image of some really cool angular unconformities. These layers below have been folded and tilted, and then the environment changed, leading to this contact layer here, and these more flat layers were deposited on top. So you could actually put the order of deposition such that you have the bottom layers deposited first, then you have the event that folded the rocks, that happened next, and then you have the top layers. And this gives you an order for the events that happen. This allows you to determine that before the layers are on top were deposited, the environment was folding and bending these rocks, and then something changed and new layers were deposited on top. Okay? Non-conformities are these areas where granite or metamorphic rocks have been deposited. They basically don't form layers. So they're kind of a giveaway here that they have no layers. They're usually igneous or metamorphic. I can pronounce words. And the environment is igneous or metamorphic, obviously. And so, and then over time, the environment will shift into one that promotes more sedimentary deposition. So this indicates a change in environment from something that creates metamorphic rock or igneous rock into an environment that promotes the formation of sedimentary rocks. So if you see here in the image that I've kind of posted below, there are some layers here, but for the most part, this is a granite layer. And these are sedimentary limestones on top. And so what you can tell here is that the environment has changed. In this new image, the contact boundary is actually outlined for you. There's this this light granite on the bottom, and you see the white dotted line here, and then it's overlain by sedimentary chert above. Okay, so that's a non-conformity. You're going to be confusing these names quite a bit: angular, non, disconformity, which is our next one. So it's okay. That's going to happen. You just kind of have to get comfortable with getting a little bit confused by the wording. Disconformities are much harder to suss out because disconformities are essentially they're a change in sedimentary environments. And so if you see here, you've got these limestones depositing over here. And over time, the environment dries out. And you get this, a change into, I think it's maybe warmer because the rocks are oxidizing. And so you've got more contact with the air above it. And then the erosion is kicking up because what happens is over time, some of those layers at the top will get eroded and then the environment will change again into another sedimentary environment. And this will lead to a disconformity, an unconformity in the rock record. There will be some missing time for where you had the erosion happening, but visually speaking, you really can't tell. What you need is what we're going to get into in the next few days. You need radioactive dating. So you might find that the rocks below are, say, 150 million years old, and then directly above it, the rocks will be something like 100 million years old, and you're missing 50 million years of the rock record, okay? And you can't really visually tell, but you can find out when you actually use radioactive dating to find the ages. This is an example here of a disconformity. There's sedimentary rocks on the bottom. You see here that's Cambrian limestone. Then you see some Devonian sedimentary rocks. And then above them, you see some Mississippian limestone. And it's hard to tell because we haven't, oh God, I can't spell. We haven't really gotten into MISSI, PPI. Yeah, I still have to do that. We haven't really gotten into these exact time periods, but so for now, you'll have to trust me that there is a gap in the record here. But see how it's not visually obvious that that's the case, but if you were to actually find the age dates, you'd find missing layers, which leads me to one of the most interesting things that we have in geology. I know I've mentioned this before, but there is something in this rock layer here at the Grand Canyon called the Great Unconformity. So there's this angular unconformity right here. There's an angular unconformity that forms this boundary. See how these rock layers are tilted and these above are pretty flat? Well, the rocks below the unconformity are about 1.1 billion years old. And the rocks above it are about 540 million years old. That's 500 million years of missing rock layers. There's a huge chunk of rocks missing. And the only thing we can conclude here is that the rate of erosion must have been outpacing the rate of deposition, but that's the only information we have. So we'll talk a little bit more about the Great Unconformity and how we know about it a little bit later. So for now, just fill out the worksheet. The worksheet's basically just asking you to explain the difference between angular unconformities, nonconformities, and disconformities. So it shouldn't be too crazy. Feel free to go back to this video if you need, and I'll see everybody in class tomorrow.